Okay, so in the last video, we introduced a linear neural net. And so a linear neural net has uh, an input layer that you put in your x's, your x1, x2, down to xn. And then we have an output layer for our y's. So that's y1 through ym. And what connects them, so these are just going to be placeholders where the data is going. And then in the middle, we're going to actually have our neurons. And so what we said in the last one was we were going to keep the number of neurons equal to the number of outputs, although you don't have to. Okay, and so these would be fully connected layers. I won't go through that right now, but so this is x in Rn, and our y is in Rm, or I should say targets are in Rm. And so what is a linear map or an affine map that takes us from Rn to Rm? It is w times x plus b. Okay, so we're going to call this y. This is going to be our model output. And what are the w's? The w's are the weights attached to each edge here. And so w, what we were saying last time was wij connects cell j of the input to cell I of the output. Okay, good. And so that's so training a neural network then means that I have a bunch of x's and a bunch of targets, and I want to try to find w and b. So let me write this down. Given x1, t1, x2, t2, up to xp, tp, find w and b such that the error that's going to be on w and b is going to be the sum of the squared errors. So remember how to compute that? That's 1 to p. And then here, let's see, these could be multidimensional, so we'll say that that's ti minus yi squared. Okay, and we know, whoops, sorry about that. Writing this in terms of w and b, this would be ti minus w x I plus b. Good. And so we want to minimize the error. And how are we going to minimize the error? We do that via gradient descent. Or we can, of course. There are other methods to do it. Before we go into gradient descent, however, there is another method I want to talk about, and that is Woodrow-Hoff learning. Because remember, if you were reading along with the text, geez, I shouldn't even be doing these videos tonight. Let's see if I can get through this. All right. So what we were trying to do is have a learning algorithm that is biologically feasible. And so gradient descent itself isn't necessarily biologically feasible. We'd like to do something that is an approximation to that may be biologically feasible. And remember, the biology that we're trying to mimic is Hebb's rule, which says when an axon of cell A is near enough to excite cell B and repeatedly takes part in firing it, some growth process or metabolic change takes place in one or both cells such that AZ efficiency in as one of the cells firing B is increased. So let's see if we can do that. Okay, so getting back to where we are now. So suppose I've got a W and a B, and I want to try to use the rule. Well, what I'm going to do is I'm going to assume that, what do we mean by taking part in firing it? I'm going to assume initially that the things that the output in a signal and the desired signal are either both positive, which means that they're firing together, or both negative, which means they would be firing together. And so in that case, I would take the change to Wij to be some learning rate times my output on cell I times my input on cell J, right? So this is the edge connecting I and J, right? And so if these are firing together, then my weight is going to be increased. Okay. Now, how would I write this? Now, this, we're not actually going to use this rule because this rule will blow up on you. You can imagine, right? Because there's no accounting for the targets here. This is called an unsupervised Hebbian rule. And it's just going to blow up on us. So we do need to fix this. But before we do that, I wonder if I can write this in matrix form. And I would like to note that what happens if I take y times x as two vectors. If I take y times x, let's see, y was m dimensional and x was n dimensional, then what kind of a matrix do I get out of that? Well, y is m by 1, x transpose is 1 by n, so I'm going to get an m by n matrix out of this, and notice that that is the same size as w. And so if I look at all the possible, or if I look at all the entries here, this is going to be y1 x1, y1 x2, oops, that looks like two entries, that's multiplied together, y1 times xn, and then y2 times x1, y2 times x2, y2 times xn, ym times x1. Okay, you're seeing the pattern, I hope. Good. And so now these are exactly matching up with the weights wij. And so that's why we can say that the change in the weights as a matrix, right, we could write as alpha times y times x transpose. And remember that this is a matrix. A matrix. Good. So we can update the matrix all at once. And of course what I said was that that's going to be a terrible update. So why are we looking at it? Well, we're going to fix that problem. And the way to fix the problem is we need to take the targets into account. And the way we'll take the targets into account is we're going to take the change in w to be alpha. Alpha is a scalar, but instead of y, we're going to be using target t minus y times x transpose. Okay. Now, by the way, we have lots of x's and lots of t's laying around, right? Because we have the data there. So I have not specified which data point this is, but this is a single data point. Okay. And so this is the rule we're going to use, and then the change in the bias is very similar It's just going to be alpha times t minus y. Good. And so just to give you the algorithm now for Woodrow-Hoff learning. One. Oh, well, I should set it up first. Okay, I always like to do an error check at the beginning. So what we're given dataset X, dataset T. We might be given the learning rate. We're going to talk about the learning rate in just a second. And then the number of epochs. And an epoch is the number of passes, or one epoch represents one pass through the data. One epoch equals one pass through your data. Okay, and so we need to then initialize the W and B. That's step one. And then we'll do our loop for I equals 1 to number of epochs. For J equals 1 to number of points. Get your output. This output is equal to Wx. I'm going to use MATLAB notation. I hope you don't mind. Right, plus B. And then what do we need for our algorithm here? I've computed the y so far. I need to get the t minus y as the error. So this error is equal to t j minus this out. Right? And then you could take the error at j to be equal to the norm of this error if you want. Actually, this isn't very good pseudocode. I'm basically writing down the MATLAB code. Let's see. If you want to set your alpha, you would here. But if we're given the alpha, we'll just go ahead and do our update. Then dw is equal to alpha times this out. Whoops. Or this error, I guess is what it is. This error times your x, j transpose. And db is just going to be alpha times this error. Good. And then our w is just w plus dw. And our b is b plus db. Now, you should be shouting, wait a minute, aren't we supposed to be subtracting? Yes, we are. However, we're going to see that in the gradient descent, a negative sign pops out in front of this x right here. And so the negative of the two negatives are going to cancel, and we're going to end up being plus there. So it will work out the way this is set up. Good. This is it. This is the entire thing. This is the Woodrow-Hoff algorithm. I've already gone about 5 minutes over, so I'm going to stop here. And in the next video, we're going to be looking at the learning rate. I think we'll just take a quick look at the learning rate and then go into an example. See you then.